Did it start? Wait, has it started? Wait, testing. Wait, how come it's not showing? It's like, is it actually showing?
Yeah.
Alright, so UNSW MathSoc presents the 1231, 1241 revision seminar. This is the algebra seminar. We did the calculus seminar. This Tuesday, and the live stream is on our channel if you want to see that. So another thing we'd like to point out is there's a super revision day happening. It's happening on 5th and 6th of August, Monday and Tuesday. And which will go 10 a.m. to 4 p.m. It's in Matthews, like level 2, etc., etc. And here's a QR code if you want to scan it. Okay. This one. Alright, so yeah, here's the QR code if you want to scan it. So anyways, moving on to the seminar. So first part of seminar is vector spaces. So, and the main thing we're looking through at here is subspaces. So, So, what is a subspace? So a subspace is a subset S of a vector space V over a field, such such that subset is also a vector space. So how do we know if a subset is a vector space? Well, a subset is a subspace. Well, we know if it's a subspace if it contains this zero vector V, if it's closed under vector addition, and it's also closed under scalar multiplication. And as you can see here, here's how we define closure. It's closure under vector addition is when for any U and V in S, we have U plus V in S. And closure under scalar multiplication is just if we have a vector V in S and lambda in our field F, then lambda V is in our subspace S. So this is best illustrated with an example. So here's a past question. So suppose that we have this subspace defined like as shown. So we either want to prove that S is a subspace of R cubed or explain why it's not. So from here, what we're trying to do is either show that all three of these properties here, 1, 2, and 3 are true, or show that one is false. So let's just start with the simple question, is the zero vector in our subset S? So we note that our zero vector is in S, as 0 plus 2 times 0 is obviously greater or equal to 0. And we can also show that it's closed under vector addition. So if we consider two arbitrary vectors U and V in S, then we consider this vector U plus V, which is A plus P, B plus Q, C plus R. And we note that since A plus 2C is greater or equal to 0, and P plus 2R is greater or equal to 0, since U and V is in S, we can combine these two equations and we get that this A plus P, we can get this A plus P here plus 2 times C plus R here is greater or equal to 0. And we note that this A plus P is this thing here, our C plus R is this thing here. So our vector U plus V satisfies the conditions to be in S. And thus U plus V is in S, and thus we get that the vector we get that our subset is closed under vector addition. So nice, we have the zero vector, we have closure under vector addition, but we still need one more thing, which is closure under scalar multiplication. But the thing is, we can see it's just not closed under scalar multiplication. If we consider just this vector 1, 1, 1, we can see it's in S, since 1 plus 2 times 1 is 3, which is greater or equal to 0. But if we have the scalar -1, we get the vector, if we multiply it by our vector, we get this vector -1, -1, -1. But we note that -1 plus 2 times -1 is less than 0, since it's -3. So this vector here is not in S, and we can see that our subset S is not closed under scalar multiplication. And since it's not closed under scalar multiplication, we can see that it's not going to be a vector space or a subspace. So for here, we only really showed that like, oh, how do you show it's closed under vector addition? How do you show if there's 0 vectors in it? And we also showed a counterexample for scalar multiplication. But we didn't really show how you really like prove that it's closed under scalar multiplication. So that's mainly what this exercise is for. So how would we show something is closed under scalar multiplication? Well, consider this new set here, which satisfies this condition. So it's kind of the same thing where we consider some arbitrary vector v and some arbitrary scale, but instead of an arbitrary vector u, you consider some arbitrary scalar lambda. And you consider this vector lambda v, which is just like lambda times all the components. And we note that x squared minus y squared equals z squared, since this vector v here is in S. So we consider this vector lambda v, and we consider kind of like the left-hand side of this equation. So we can see that this left-hand side would just be lambda x squared minus lambda y squared. So what's this equal? So if we distribute it, we can like factor out the lambda squared, and we get lambda squared times x squared minus y squared. And we know that x squared minus y squared is equal to z squared. So we get that this is just lambda squared times z squared, or lambda z squared. And thus we get that this thing squared minus this thing squared is equal to this thing squared. And thus we note that this lambda v is also going to be in S, and we get that our set S is closed under scalar multiplication. So that's generally like how you would prove your subspace stuff. So yeah, moving on. We define a linear combination of some vectors v1, v2 all the way to vn, such that it's like we scale each vector by some arbitrary lambda, and that would just be a linear combination. So with this in mind, how we define our span S is just the span of a set of vectors is just the set of all linear combinations of those vectors. And something we note that if S is finite and non-empty, then the span of S is a subspace of V, and it's also the smallest subspace containing all the vectors in S. And additionally, if the span of S is just the vector space V, then S is called a spanning set. So So here's an example question to really illustrate this idea. So we consider the vectors in R3. We have this V1, we have this V2, we have this V3, and we have this B. And we have to prove that B is in the span of V1, V2, V3. And we also have to show like whether V1, V2, V3 is a spanning set of R3 or not. So how would we do this? Well, we'd use an augmented matrix. So basically the idea is we want lambda 1, lambda 2, lambda 3, such that lambda 1 v1 plus lambda 2 v2 plus lambda 3 v3 is equal to b. So we use this augmented matrix v1, v2, v3 here, and we try and solve it. And once we put it in our row echelon form, we can see that this like vector here at the end, our b at the end, is not a leading column. So there exists at least one solution to this equation, and thus we get that b is in the span of the three vectors. But we note that if instead of b here, if we consider some arbitrary vector x, y, z, then if we row reduce it, we get this matrix here. But the thing is, this only has solutions if this expression here is equal to 0. But we know that not all vectors satisfy this expression, so not all vectors could be in the span of v1, v2, v3. And since not all vectors could be in the span of v1, v2, v3, we can see that it's not a spanning set. So any questions? Okay. So, whatchamacallit? So another concept, linear. So what does it mean to be linear independent? So basically, what it means to be linearly independent is that when we have any linear okay, so if for some set S, which has like vectors v1, v2, vn, the set S is linearly independent if the only linear combination that gets you the zero vector is when our lambda 1, lambda 2 is all 0. So, and if it's not linearly independent, then it will be linearly dependent. And there's the informal definition. It's if there exists a vector in S that is a linear combination of the other vectors, then the set is linearly dependent. And if there are no such vectors, then S is linearly independent. So it's just a few definitions. I'm sure you've seen them before. And a few other things is that if we have the zero vector in any set of vectors, then the set is linearly dependent. And if two vectors are linearly independent, they are not equal, nor are they parallel. And I think what's the most useful thing here is that for linear independence and linear dependence, it's that when we consider the matrix v1, v2 when we consider the matrix with column vectors v1, v2, vn, when we put it in row echelon form, the set is linearly independent if there are no non-leading columns. And if non-leading columns exist, then the set is linearly dependent. And another way you can do it is if we look at the determinant of the matrix. And if the determinant is 0, the vectors are linearly dependent. And if the determinant isn't 0, then the set is linearly independent. So basically what this is saying, we can just put our vectors in the matrix and we can figure out whether our vectors are linearly independent or not from this matrix. So here's an example question about linear independence. So we consider some basis B, which has vectors u, w, u, v, and w. We consider some B with vectors u, v, w in R cubed, such that the vectors are linearly independent. And we consider these three sets here. And so our goal here is, for each of S1, S2, and S3, we have to determine whether they are linearly independent sets or not. So how do we do this? So the main idea here, just like before we go straight into the solution, the main idea here is that we want to use that this set B is linearly independent. We want to use that the only solution to lambda u, okay, that's not good. So the only solution to lambda 1 u plus lambda 2 v plus lambda 3 w is equal to 0. We want to use that. The only solution to this is when lambda 1, lambda 2, and lambda 3 are equal to 0. So what does that look like? So for S1, which is just the set of the vector u minus v, we consider this equation lambda times u minus v is equal to 0. So since B is linearly independent, we get that u and v aren't equal, so u minus v is non-zero vector. And thus we get that S1 is linearly independent since the only solution for lambda is lambda equals 0. And for S2, we can do this similarly, where we consider the equation where a linear combination is equal to 0, and we rearrange these coefficients such that they're separated for each vector, basically. So since we know that B is linearly independent, we get that this lambda 1 here, this lambda 2 minus lambda 1 here, and this minus lambda 2 all must be 0. So from there, we get that our lambda 1 and lambda 2 are both 0, and the only solution for this equation would just be lambda 1 equals lambda 2 is equal to 0. And so we get that our S2 is linearly independent. So do you have any questions here? Or okay. So finally, for S3, we have U minus V, V minus W, W minus U. And now we consider some linear combination such that it sums to 0. And if we rearrange it, we get that lambda 1 minus lambda 3 times U plus lambda 2 minus lambda 1 V plus lambda 3 minus lambda 2 W is equal to 0. And since B is linearly independent, it means that there are only solutions if we get that this is equal to 0, this is equal to 0, and this is equal to 0. But we can see that like they're all 0 if and only if lambda 1 is equal to lambda 2 is equal to lambda 3. And there's no other conditions. So like let's say they're all equal to 1. We can see that U minus V plus V minus W plus W minus U is just equal to 0. And we find a solution for our lambda 1, lambda 2, and lambda 3, which such that not all of them are 0. And since we found such a solution, we get that S3 is not linearly independent. And thus, S3 is linearly dependent. So does that make sense? Okay. So moving on. So let's look into bases and dimensions. So if we have some B, if B is a set of vectors for a vector space V, if B is both linearly independent and a spanning set for V, then B is called a basis. And we just denote the dimension as the number of vectors in any basis. So the set cannot be linearly independent if there are more vectors than dimensions in the set. That's just another thing to note. And a really like common thing that happens is use this like mini little lemma here, and it's basically like buy two get one free in a sense. So if any two of the conditions are true, then the third one's also true. So 1 and 2 imply 3, 3 and 1 imply 2, 2 and 3 imply 1. So I feel like it's best illustrated through an example. It's kind of weird, but so we consider this like funky field F, which we call GF4, with the 4 elements 0, 1, alpha, and beta. And we have addition and multiplication defined as such here. So we want to show that, first we want to show that B1, B2, B3 is a basis for F3. So how do we do this? Well, we put it in row echelon form. And after we put in row echelon form, we can see that each column is a leading column, and there are no non-leading columns. And the set is linearly independent for, so the set is linearly independent. And we note that F3 has a dimension of 3. And since there are 3 vectors in the set, we note that, how do you phrase it? We note that there are 3 vectors in the set. We also note that the dimension of this is 3. So we get that, this condition 1 is satisfied. We note that from before, from the matrix, we get this condition 2. The set is linearly independent. It's also satisfied. So that means that this third thing is true. We also know that the set is a spanning set for V. And what does that mean? It means it's a basis. So we get it's a basis from there. Do you want me to row reduce this? Would it help if I do you want me to row reduce this, or? Yeah. Do we all buy it? Do we all think it's true? Yeah, sure. Yeah, okay. So, anyways, moving on. So here's part B, and we have to explain why this set is a spanning set, and we also have to explain why it's not a basis. Well, first things first, we note that the dimension of F3 is 3, and the set is 4 vectors. So it just can't be a basis since since there are just more vectors than the dimension. So now we'll try and show it's a spanning set. So we'll consider some linear combination of this set, and we can just arrange it to have like just coefficients in front of b1, b2, and b3. So now we're trying to show that for some arbitrary linear combination, mu1 b1 plus mu2 b2 plus mu3 b3, we can get that this is equal to mu1, this is equal to mu2, and this is equal to mu3. Well, so how would we do this? We just like consider some substitutions, some magic substitutions. So here we'll just like lambda 1 is equal to mu1, lambda 2 is 0, lambda 3 is mu2, and lambda 4 is mu3 minus mu2. And we can see that each of these brackets turn into mu1, this one turns into mu2, and this one turns into mu3. And so any linear combination of b1, b2, and b3 is going to be in the span of this set here. So we note that the span of this set here is a superset of the span of b1, b2, b3. But we know that b1, b2, b3 is a basis for our, we know that b1, b2, b3 is a basis for our vector space F3. So we know that it's a spanning set. So since it's a spanning set, we also know that our other set here is also a spanning set. And yeah, and then we're done. So are we fine with that? Okay. So one last thing to touch upon, just coordinate vectors. So if we have a vector v, which we can represent as a linear combination of a basis, then the coefficients required to make v make the coordinate vector. It's kind of it's hard to show without an example. So we'll just like go through this one pretty fast. So we just want to find a coordinate vector of this vector with respect to this basis. And how we do that, again, we just do an augmented matrix. So the premise here is that we're trying to find solutions to this. So lambda 1 b1 plus lambda 2 b2 plus lambda 3 b3 is equal to v, because then our lambda 1, lambda 2, lambda 3 is our coordinate vector for v with respect to the basis. So if we want to solve this, we put it, we make an augmented matrix with these vectors, and then we put it in row echelon form. And we get to this here after putting it in Maple. And from there, we can just back substitute, and we find that lambda 1 is 3, lambda 2 is -1, and lambda 3 is 2. And from there, we can get our desired coordinate vector, which is 3 minus 1, 2. So that makes sense? Okay. So moving on to part 2, linear transformations. So what is a linear transformation? So linear transformation is just a function that takes in a vector and outputs a vector, such that it preserves vector addition and scalar multiplication. And also note that linear transformations only exist from one vector space to another vector space. So another way we could show this is just if we have that t lambda u plus t lambda u plus mu v is equal to lambda tu plus mu tv. And yeah, again here that v and w just must be vector spaces. So here's just an example. We consider this mapping defined like this, from polynomials of degree 2 to polynomials of degree 3. And polynomials of degree at most 2 to polynomials of degree at most 3. And we have to show that T is a linear transformation. Well, okay, so first off, so we kind of, if you looked into the past papers for 1241, one of the questions is just claims that differentiation is a linear transformation. But you can kind of see that it is, because like if we diff two things, if it's like d on dx, u plus v, this is equal to du on dx plus dv on dx. And so we get its preserves vector addition. It preserves addition. And also if we multiply, if we diff something multiplied by a scalar, so d on dx lambda u, we can also see that this is just kind of lambda times d on dx of u. And we can see it also preserves scalar multiplication. So we kind of just like, we basically kind of observe that, yeah, differentiation is just a linear transformation. So from there, we can just consider some arbitrary polynomials u and v, and some scalar lambda. And from there, we can just like kind of bash it out. We can kind of expand it and rearrange it. And we can see that t of u plus v is equal to t of u plus t of v. And additionally, we can see that t of lambda v is equal to lambda times t of v. So from here, we can see, from this thing here, we can see it preserves vector addition. And from this thing here, we can see it preserves scalar multiplication. And since it preserves the two, and we note that this is a vector space, this is a vector space, we get that T is a linear transformation. So we're happy with that? Okay. So another thing with linear transformations, we can also kind of represent them geometrically. So we consider some linear map from the Cartesian plane that maps back to the Cartesian plane, where it reflects a vector in the line y is equal to root 3x. And we have to show that these two things, basically. So one thing that you might notice is that if we consider y on x, this is equal to root 3. But what's also root 3? This is tan of 60 degrees, or tan of pi on 3. So we get that this angle here is pi on 3. So if we consider some reflection, right? So if we reflect this vector here, if we just consider the vector 1, 0, it will get reflected to this vector here. And since reflection preserves length, this thing will have a length 1, but this angle here will be 2 pi. So, 2 pi and 3. So do we kind of buy that? And another thing is, similarly, we get that if we take this vector here, we take some vector here, which is 0, 1, and then we reflect it over here, then the angle will be, if we have this here, then the angle will be pi on 6. So do we get that? Do we buy that as well? So from there, we get that this length here will just be cos 2 pi on 3, and this will be sine 2 pi on 3. And similarly, this will be cos, this thing here will just be cos pi on 6 and sine pi on 6. And if we just evaluate these values, we get that it's minus 1/2 root 3 on 2 and root 3 on 2 1/2, like we wanted from the question. So do we understand that? Okay. So, and one thing to point out here, just a little interlude, it's that linear maps are just matrices. So basically, we have that any matrix is a linear map. We can see it like matrices are a vector space, and like matrix addition and scalar multiplication, like kind of preserved. And also that every linear map, any linear map can be represented by a matrix. So we note that these two things, there's like a bijection from the two sets. So we can illustrate with this with an example. We have this matrix here, And we can see that it's also this mapping T, this linear map T, which maps our vectors from R3 to R such that it's it's just these values. So where does that come in with this question? So what we want to find is a linear, we want for our linear map T, which we found earlier, we want to find a matrix A such that AX is equal to T of X for all X in R2. So we note that our standard basis for R squared is just this, and we note that if we found like the images of our standard basis vectors under our linear transformation T. So from the matrix representation theorem, which we saw earlier, we get that our A is just equal to this 2 by 2 matrix. And so with this in mind, if we were to find, for example, the image of vector 4, 5 under this linear transformation, we can do this two ways. Well, the first way is we already know these standard bases. We already know the images of these standard bases, and we can just since we know it's linear, we know it preserves scalar multiplication and vector addition. So we get our T of 4, 5 is equal to 4 times T of 1, 0 plus 5 times T of 0, 1. And we know these two values already. So we can just plug them in and we get this equal to this plus this, which is equal to this. But we can also use the matrix we found earlier. We note that our transformation T is equal to A times this, which is equal to this matrix times this, and with just some matrix multiplication shenanigans, we get that it's equal to this matrix, this vector here. So are we happy with that? Okay. And so here's another question. We have some vector space V and W, and we have T be a linear transformation. So we have to prove that if under this linear transformation for some vectors v1, v2, dot, 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 vn, if under this image they are linearly independent, then they are linearly independent they're linearly independent before passing through the mapping. And part B is the converse true though, basically. So just going through part A first, we just consider the linear combination such that lambda 1 v1 plus lambda 2 v2 plus dot 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 plus lambda n vn is equal to the 0 vector in V. So we know that the 0 vector in W is equal to T of the 0 vector in V. That's just something about linear transformations. So it's equal to T of this, which is equal to T of this. And we can just kind of expand them out since it preserves vector addition and scalar multiplication. We can just expand it out. We get this plus this plus this plus this. But since TV1, TV2, and dot 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 TVN are all linearly independent, the only solution to this is when our lambda 1, lambda 2, dot dot dot, lambda n are all 0. So it means that the only solution for this to also equal 0 is when the lambdas are all 0. And thus our original vectors v1, v2, dot dot vn are also linearly independent. So we understand? Okay. But let's consider the converse. If v1, v2, dot 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 vn are linearly independent, then tv1, tv2, dot 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 tvn are linearly independent. Is this statement true or false? Is the converse to the original statement true or false? Well, in fact, it's actually false. So we can just consider some linear transformation here. We consider T of x is equal to x1 minus x2 for some vector x1, x2. We note that we can kind of just see that our vectors 1, 0, and 0, 1 are linearly independent. But under this transformation, they become the same vector. So under this transformation, they're linearly dependent. So that means that even if our v1, v2, vn is linearly independent, this does not necessarily mean under the transformation they will also be linearly independent. Does that make sense? Okay. And okay, so we'll go through a few more definitions here. So kernel and nullity. So for some linear map, so for some linear map or some matrix, the kernel will just be the set of all vectors that get you the zero vector, essentially. And the kernel of a linear transformation is always a subspace of V, and the nullity is just the dimension of the kernel. And so okay, so just a small example here. So we're given this maple stuff. I'm sure you've seen some sort of these questions before. You're given this maple stuff, and we have to find a basis for the kernel of A. So we can find a kernel by solving this augmented matrix A with the zero vector, as we want to know what vectors give us the zero vector. But, Maple's done that. Maple's done the linear solve for us. So here we have variables t3 and t5. Instead, let's just call them alpha and mu, just because we're more familiar with those variables, I guess. So we get that our kernel A is equal to this, which we can parameterize to get lambda times this vector plus mu times this vector. And we can kind of just observe that these two vectors are linearly independent, and thus they make up the span of the kernel, and hence they must be its basis. So it makes sense? Okay. And similarly, just more definitions, the image and rank. You can kind of consider these like image and rank with kernel and nullity, they kind of come as a pair. So what is an image? So image is basically, for a linear transformation or a matrix, the image is basically all the possible all the possible outputs you could get, all the possible vectors you could possibly get. So you could kind of think of it as the range of a linear transformation. And what a rank is, oh wait, I forgot. So also, similarly to the kernel, the image is also a subspace of V. And the rank is just the dimension of the image. So as you can see here, yeah, whatever. So now we have this question. Now the question becomes, how do we find the rank? How do we find the nullity? And how do we find the image? How do we find a kernel, right? So how do we find the rank and nullity of a matrix? Well, we would put it in row echelon form. The number of non-leading columns is the nullity, and the number of leading columns is the rank. And so if we want to find the basis of a kernel, we solve the augmented matrix, as you've seen before. And then we can develop a basis for the image by just looking at which, under our row echelon form, which columns are leading columns, and just take those columns to be our basis for the image. And just from this, you can kind of deduce the rank nullity theorem, which is the rank of T plus the nullity is just the dimension of V, or for some matrix A, the rank of A plus the nullity of A is just the number of columns of A. So let's look at it with respect to this question here. So we're given some matrix, and we just have to find all the vectors that belong to the image, find a basis, and we have to find the rank nullity, and we have to find just basically just determining some properties of this matrix. So let's just look at part A for now. So if we want to find all vectors that belong to the image of D, we can augment our matrix D. We can augment our matrix D with B, and then by multiplying our second row by 3, multiplying our third row by 2, we can get this matrix here. And that means since these two rows are exactly the same, we need the condition that these two things are exactly the same as well. So the condition for a vector to be in the image of this matrix is just that 3 times 2b is equal to 2 times 3 times b2 is equal to 2 times b3. And this is just a plane that contains all the vectors that belong to the image. And so if we're trying to find a basis for the image, we can just take the row echelon form and see what matrix we get. And we can see that these two columns, they're leading columns. This one isn't a leading column. So we just take these first two columns, the vectors in those first two columns, to be our basis. So we just take this first column, the second column, and this forms a basis for the image of D. And you can see just the basis here. And yeah, if you've done your lab test too, you kind of know how to do this. So now we'll just state the rank and nullity of D. So we know from before, right, that the basis for the image of D was given by this, and it has 2 vectors. So the rank of D is just 2. And from rank nullity theorem, since there's 3 columns, we get that 2 plus our nullity is 3. So our nullity of D is just 1. And from there, we can look to find a basis of R3 that contains B. So we already have this basis for our image, but we just need one more vector. So for this to be a basis, we basically need a third vector that is linearly independent to both of the vectors. So an easy way to do this is just to take the cross product of the 2 vectors. And if you evaluate it, the cross product will just be this vector 0, 15, 10. And thus we get this basis here. So do we all understand? Are there any questions?
When you say independent, is it independent from like everything? Or is it like independent but like you still make the vectors with it?
Oh, like as in like we just want a third vector that like such that the set, well, we're basically just trying to find a third vector v3 such that these 2 plus v3 is a linearly independent set.
Okay, so what's this original basis here?
What's this original basis?
The 0, 2, what's that from?
It was the basis of the image.
Oh, and then we're adding that extra one. Okay.
Yeah, we just want to, so the question is basically asking, we have this basis for our image. And like what basis can we make with those 2 vectors in it? So we just want a third vector that's just basically not pointing in the same direction. We basically just want a third vector such that this like set of 3 vectors is not linear, is linearly independent or not linearly dependent.
Okay, so we can find the basis of R3 through the image of the basis of the image.
Wait, what was the question? Wait.
So we can find the basis of R3 through the basis from the image of the image.
Well, like, how do you describe it? Well, wait, what exactly is your question? Because like.
So that basis, the original basis is from the image, right?
Yeah.
So we can use that image basis to find the basis for R3.
Well, we don't really need to we don't really need to find a basis for R3 using this because we already know a trivial basis, which is the standard basis, like 1, 0, 0. The question here is just asking us like, okay, here are 2 vectors. If we're like, what third vector do you want to add to make this a basis? That's basically the question. Okay, that's fine. All right, and I'm pretty sure that's the last question. So, okay, eigenvalues and eigenvectors. I'm not gonna lie, I'm kind of cooked. But okay, so how do we define eigenvalues, eigenvectors? So if A is an n by n square matrix, and if we have a scalar lambda in our field F, and we have a vector and a non-zero vector in Fn, if we have that A times V is equal to lambda times V, then lambda is an eigenvalue of A, and V is a corresponding eigenvector of A. And you can kind of see here, basically, if we consider our A as some like transformation in the plane, eigenvectors are vectors that will just like stay parallel, like point in the same direction basically. And eigenvalues are just like how much each eigenvectors gets scaled by. So how do we get eigenvalues and eigenvectors? So we get it if we get our eigenvalue lambda is an eigenvalue of A, if and only if the determinant of A minus lambda I is equal to 0, and V is an eigenvector of A that corresponds to lambda, if and only if A minus lambda I times V is equal to 0, where V is not a 0 vector. And just some like extra terminology, we call this determinant, we call this here like the characteristic polynomial of degree n in lambda. And the eigenspace of A corresponding to lambda is just the set of whatchamacallit, it's a set of eigenvectors with that with the eigenvalue. And it is also a subspace of Fn. And we can prove it with the subspace theorem. So here's just some true definition. Yeah. Are fine to move on? Okay. So first things first, existence of eigenvalues. So our n by n matrix has exactly n eigenvalues if we have real and complex eigenvalues are counted, and if like eigenvalues are accounted according to their multiplicity. And we kind of like see this is true with like if we consider our characteristic polynomials, and if we consider like if we include like complex numbers, there will be exactly n roots and stuff. And another theorem is just if our matrix A has distinct eigenvalues for each eigenvector, then each of the eigenvectors are linearly independent. So are we fine to move on? Or?
What do you mean it says real and complex vectors are counted? Like it has one real and one complex?
Oh, like okay. So for like, how do you describe? It's like, how do you describe it? It's whatchamacallit? Ooh. It's because like you consider your characteristic polynomial, and then you consider the characteristic polynomial of A minus lambda I. So the solutions for this to be 0. Like for example, like if our A is just like the vector, I don't know, 1, 2, 3, 4 or something, and then we want the solutions such that this minus lambda I, which is equal to 1 minus lambda. Okay, actually, no, I'm not explaining it well. No. That. Yeah, I feel like it's not too complicated. The premise is basically like if you consider the characteristic polynomial of like A minus lambda I, then it has a degree of n, and since it has a degree of n, it will have exactly n roots. Mm-hmm. But like that's only true if you count complex roots and if you count multiplicity. It's like something from 1141. Yeah, sorry. I feel like I couldn't explain it. Yeah, I just can't explain it well. Sorry. So, diagonalization. Okay, why is this? Okay, anyways. So, it should be this. Why is it? Okay, it should be M inverse. Okay. So, given A is an n by n matrix with n linearly independent eigenvectors, there exists an invertible matrix and and diagonal matrix D such that like A plus M inverse dm. Well, A equals M inverse times D times M, where the diagonal entries of D are the eigenvalues of A, and the columns of M are the corresponding eigenvectors of A. And we get that A is diagonalizable if and only if it has n linearly independent eigenvectors. And yeah. sorry. So you can we'll demonstrate with this example question here. So let's C equal to this like matrix here, and we have to find the corresponding eigenvalues of C, and for each eigenvalue find the corresponding eigenvector, and we also have to find, is C actually diagonalizable? So let's just look at just part one for now. So our matrix C, if we consider the characteristic polynomial, we have the determinant of C minus lambda I is just equal to the determinant of this. And if we like just expand it, we get it's this, which is equal to this. Or this is equal to, okay, and which is also equal to lambda minus 3 squared, as you can see. And so we can see that there's only going to be one eigenvalue, which is lambda is equal to 3. And then to solve and to find the eigenvectors, we solve this is equal to 0. And lambda has to be since lambda has to be an eigenvalue here, and 3 is our only eigenvalue, we have to solve this vector equation C minus 3i is equal to 0. And from there, you get this augmented matrix. You augment the matrix C minus 3i with the 0 vector, and we get this. And we can row reduce it to get this vector here. This matrix here. And so we get that our eigenvectors are in the form of v2 is equal to t, v1 is equal to t, for v is equal to v1, v2. And we get that all our eigenvectors for lambda equals 3 is just a scalar multiplied by this vector 1, 1. Do you understand that? Okay. So from there, we only get one eigenvalue, lambda is equal to 3, and there's only one corresponding eigenvector, which is like t scalar times 1, 1.
Just a quick question. When you say so v2 equals t, you just let v2. Are you looking from like the second row, or is it only from the first row?
Well, what do you mean?
Was to find v2 and v1, because if v2 equals t, doesn't that mean just negative 2? Oh wait. Yeah, never mind.
Yeah, but yeah, okay. You got it?
Yeah.
Yeah, okay. So you understand this? So yeah, so anyways, we get like one eigenvalue, which is lambda equals 3, and we only get our corresponding eigenvectors are scalar times, like the vector 1, 1. But so for part two, whether the vector, whether our matrix is diagonalizable or not, we note that for M, it has to have, the columns of M have to be eigenvectors, but note that all our eigenvectors are in this form, and thus our eigenvectors aren't linearly independent, right? And since they're not linearly independent, we get that the determinant of our matrix M is going to be 0, and thus it won't have an inverse, right? Do we get that? Yeah. So that's basically this argument here, and thus it's a defective matrix. And another reason we consider diagonalization, well, I think this is the main reason. It's that it's so much easier to power matrices. Because if we consider this thing here, this should be M inverse, sorry. It's M inverse, and should be just M.
What's the difference in changing the things? It looks like they should be the same.
No, it's because order matters when you multiply matrices, right? Because if you have because when we multiply matrices, just it's this one uses the rows, this one uses the columns. So a matrix A multiplied by B is not necessarily equal to B multiplied by A. So that's why the order matters. So anyways, going on here, we basically, but the like general, even though it's like the wrong way around, the general idea remains the same, where a to the k is equal to m inverse d to the k times m. So the thing about this is that powering diagonal matrices is very easy because we can just power the components on the diagonal, like power the entries in the diagonal. So that's why we kind of diagonalize matrices. And a quick example with this is, okay, so yeah. Wait, is it? Wait. Okay, this might be the right way actually, I forgot. But like, I'll think about it. So evaluate, so here you have an example here. Evaluate A4 using eigenvectors where A is equal to this. So we have to determine the eigenvalues and eigenvectors. So how we do that, we consider the, characteristic polynomial. So this characteristic polynomial will just be 2 minus lambda times 3 minus lambda minus 2 times 1. And you can get it this, and you can factor it to the here. And we have eigenvalues of 4 and 1. And we can just like find that the respective eigenvectors are going to be in, so we can find respective eigenvectors of 1 and minus 2. All right? Yeah. Yo.
What?
I swiped, bro. Okay. My bad, sorry. So, yeah, eigenvalues. So we have eigenvalues 4 and 1, and we find some eigenvectors for them, which is 1, 1, and minus 2, 1. So from there, we get Rm is just going to be 1, 1, minus 2, 1. Rd is going to be the eigenvalues, which is 4, 1. It's diagonal matrix with entries 4 and 1. And we can just compute our M inverse from knowing what our M is. And it's just going to be this. And thus, we can kind of like collapse the multiplication and solve. So we get that a to the 4 is equal to m times d to the 4 times n inverse. Or a to the 4 is equal to this times this times this. And you can just kind of compute it really easily. And we get this. So we kind of understand how this works. All right. And this is, oh my God, this question. So basically, we have a real n by n polynomial with n distinct eigenvalues. And it can be expressed, it can be diagonalized, basically. So we have the characteristic polynomial P of x of A as this. And by replacing x with a matrix D and A0 with A0 times the identity matrix, we have to prove that P of D is equal to this P of D is equal to the n by n zero matrix. So the way we do it is we just like first things first, we just kind of like note what is the characteristic polynomial of our matrix A. It's just a polynomial which has our eigenvalues, lambda 1, lambda 2, lambda n, as the n solutions to the polynomial. So if we replace this by d, we get this. And we note that every term in the polynomial is a diagonal matrix, and P of D is a diagonal matrix. So we can kind of like compute each of the entries of our diagonal matrix. So if we just consider our D is equal to lambda 1, 0, 0, lambda 2, ... we can just consider this lambda 1 for now, just to make things easier. So if we consider just the top left entries, the top left entry of this thing here, we get that the top left entry will just be lambda 1 to the n plus a n minus 1, lambda 1 to the n minus 1 plus plus a1 lambda plus a0. So from here, we note that this. So we note that since lambda 1 is a solution to this, we know that this is equal to 0. And so our top left entry will be 0. So do we kind of see that? Okay. So we can use like a similar argument. And we can kind of use, we can use a similar argument and kind of show that, like, you know, that the second entry is also 0. That all the entry, and then like that all the entries on the diagonal are all 0. And since all the entries on the diagonal are 0, our P of D is a diagonal matrix. We get that it's also the 0 matrix. So therefore, we get that P of D is equal to 0. Right? Do you understand? Okay. And so for part 2, we also want to show that P of A is equal to 0. So how can we do this? We know that from before that our A to the K is just equal to M times D to the K times N inverse. So P of A is equal to P of this. And thus we get it's equal to M D to the N M inverse plus A N minus 1 M dot dot dot. So we can basically extract this M at the front. We can put it at the front. And we can extract this M inverse at the back, and we can put it at the back. And we have this thing here. But we know from before that this thing here is just P of D. And what's P of D? It's just a 0 matrix. And since it's a 0 matrix, it like basically kills these two, and it's still the 0 matrix. And so we get that our P of A is also the 0 matrix. And yeah, does this make sense? Okay. So we let A equal to this.
Does P in this situation like mean probability, or is it just?
It's like a polynomial.
Oh, okay.
Yeah. So we let A equal to this. So okay, what's the third question? So just like our refresher. So we use this result in 2 to show that this matrix satisfies this. So from here, what is the characteristic polynomial of our A? We get the characteristic polynomial of A is this lambda squared minus lambda minus 6. So we also note that our A must satisfy this from above. So we get that our A squared minus A minus 6i is equal to 0, or A squared plus is equal to A plus 6i, where I is the identity matrix. All right, does this make sense? Okay, so just like one last thing. So one more thing we can use these eigenvectors for is just solutions of differential equations. We basically get that this is a non-zero solution of this if and only if A has the eigenvalue of lambda. And the general solution will just be like a linear combination of these things. Yeah, that's basically it. And yeah, so final examples, we solve the system, we solve these two we solve this system of equation here, and we'll solve this equation here. So let's first look at this system, this first order ODE system. So we let y is equal to like this vector xy, and we let a equal to this. And it's the coefficients of, you can kind of see that it's just the coefficients of this system. So and thus its equivalent to dy and dt is equal to this matrix times y. And we can solve for the characteristic polynomial for this matrix A. We get that it's equal to lambda minus 2 times lambda minus 3. And thus we get two eigenvalues, lambda 2 and lambda 3. And we can find some corresponding eigenvectors for them, which is like 1, 1, and 2, 1. And hence we get two linearly independent solutions, which is y is equal to e to the 2t times 1, 1, and y is equal to e to the 3t times 2, 1. And we note that a general solution will be a linear combination of these. So y is equal to a times e to the 2t 1, 1 plus b e to the 3t times 2, 1. And since we note that we had our y is equal to our vector xy, if we just like consider the values on the top, we get our x is equal to this. We consider our values at the bottom, we get y is equal to this for some real constants a and b. So you kind of see it, or do you want me to explain it more?
Wait, do you let E equals 2
Math1231.
Yo, yeah.
Yeah.
Wait, go ahead.
Do you let you always have wait, you always have to make do you always have to have it be e to the power of like the eigenvalues?
Yes. And I'll be honest, I just like I don't really know why I accept it as truth.
Okay.
Yeah. It's just like it's yeah.
It just is.
It just is. So we can kind of do something similar here, where we solve this equation, we solve this differential equation. So instead of having x and y, we can have this y1 and y2, where y1 is just y, but we let our y2 be the derivative of y with respect to t. And so we can we can kind of see that like d on dt y1 is just y2. But from this equation, if we move all of this to the other side, we get dy2 on dt is equal to 24y1 plus 2y2. Okay. And so similarly to before, we can obtain a coefficient matrix from this, which will be this. And we know that this times y is equal to dy on dt, where y is our vector here. Do we kind of see it? Do we kind of like understand the premise of this, or do you want me to explain it more?
How did we get the 1 and 2?
Well, what do you mean? What do you mean?
Okay, no.
Wait, so do you understand it? Okay. So from here, we can solve the coefficient matrix, and we get the eigenvectors and eigenvalues. We get eigenvalue lambda equals 6, lambda equals -4, and we get the corresponding vectors 1, 6, 1, -4. And thus we get the general solution for our vector y, which is y1, y2. It's equal to this for constant c and d. But we note that we just want our value y, which is equal to y1. So we just consider the top of this. We consider the top of this, the top entry of these vectors, and we get that our y1, which is y, is equal to this value here. So do we understand? Do you want me to explain it more? Is it good? All right. Yeah.
All right. Hello. All right. So the next section we're doing probability and statistics. Just a few quick definitions. Probability. A probability on a sample space S is a function P such that S goes to R with the following properties, okay? So here's just the following properties. Obviously, you would want all your probabilities to be between 0 and 1, otherwise it wouldn't make any sense. The probability of the empty set is 0, so that's the probability of nothing happening. And the probability of S happening, which is the entire sample space, is just 1. The probability of A or B is equal to the probability of A plus the probability of B for all disjoint AB, which is to say that A and B don't share anything in common. And then we move on to some more fundamental rules. P of A complement is equal to 1 minus P of A. A complement essentially just means not A, right? So 1 minus the probability of A would give me the probability that A doesn't happen, so A complement. And then P, A, or B, and this is, you'll realize it's a more generalized form of the one we had above. This should be equal to P of A plus P of B minus P of A and B. And then if A is a subset of B, then the probability of A occurring should definitely be smaller than the probability of B occurring. This is pretty obvious. And then lastly, if S is finite, when I sum up all my probabilities, it should be equal to 1. Okay, next we have conditional probability. What conditional probability means is essentially this PA with the line in the middle B means that given some event B happening, I want to find the probability of A happening given that this event B has already occurred, right? And we have a formula for this. We have it listed here. It's equal to P of A and B over the P of probability of B happening. And yeah, we'll see here says probability of A under the assumption that B has occurred. With these problems, sometimes it might help a little if you draw a tree diagram out, but typically you don't need to. We'll work through some of these later. Some important rules regarding conditional probability. So the first one is P of A and B is equal to P of A given B times P of B. If we look above, back here, it's just simply multiplying P of B from beneath. You just multiply it across, right? And same thing for is equal to P of B given A, PA. You just multiply PA over and we get that. Next, we have the total probability rule, which is to say, when we have B1, B2, all the way to Bn, when these things partition S, so they separate this sample space S into these n parts, when I add up all of these probabilities, so given that B1 has happened, what is the probability of A happening? Given B2 has happened, what is the probability of A happening? All the way to given Bn has happened, what is the probability of A happening? When I add up all of these probabilities, it is simply just the probability of A happening. And then lastly, we have Bayes' rule, which essentially just relates the probability of A given B to the probability of B given A. So in a sense, these probabilities are kind of related in a sense. So these two events, B given A and A given B, are related by this rule. And this rule is a consequence of the multiplication rule once again, right? If we look at the multiplication rule, we just reorder it around and we'll get the Bayes' rule. Okay, next we have mutual independence. So we want to know when some things are mutually independent, yeah? And then the condition for things to be mutually independent is if the probability of A and B is equal to the probability of A times the probability of B. We can extend this concept to when we have multiple events like A1, A2, blah, 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 AK. It works for more than just two events. And this is also similar to saying probability of A is equal to the probability of A given B, or the probability of B is equal to the probability of B given A, because even though I'm given B, it shouldn't affect my probability of A happening, if that makes sense. And same if I'm given A, it shouldn't affect the probability of B happening, because they are independent of each other, which means either one happening shouldn't affect the other. Okay, next, we'll just go on with the question. There's a conditional probability question here. So, take a read. A particular diagnostic test is 99% correct when a person has the disease, 95% correct when the person does not have the disease. In a population, 2% have the disease. Compute the probability that the person has the disease, given that the test was positive. Alright, so this is essentially what we had before, right? PA given B. Which try to identify what these events are, right? Like my A and B, what's my A, what's my B? My B in this case, given that the test was positive, right? That's the event that I'm given. So that's my B. My A is the person has the disease, right? So this is equal to P of A and B over the probability of B happening, right? If I want to find the probability of A and B, that means I want to find the probability that someone has the disease and tested positive, right? So when a person has the disease, or only 0.02%, or sorry, only 2% of the population have the disease, which corresponds to 0.02, right? And when the person also needs to test positive for A and B, right? So that should be 0.02 times 0.99 over the total probability of a positive test, right? A positive test either occurs when I have this case here, right? When someone has the disease and tests positive, so 0.02 times 0.99. But we also have to add the case where someone doesn't have the disease but still could test positive, right? When someone doesn't have the disease, that's the other 98% of the population, so 0.98 times by 0.05, right? We times by 0.05 in this case because the test is incorrect when they test positive, right? Because they don't have the disease. And here in the solutions, we kind of did it a different way, but they drew a tree diagram. It might be impractical to draw a tree diagram for more complicated cases, but this case is simple enough. We can draw a tree diagram to help us understand what's kind of going on here. So firstly, they split it off into having the disease or not having the disease, right? Disease and disease complement. And then from there on, we split it into test positive and test negative, right? T being positive, T complement being negative, right? So here we can see that if we just look at the tree diagram and we apply all of these rules, right? We'll just find that P of D and T is simply just this thing here, right? And then we just get that by multiplying the two probabilities along that branch, kind of, right? And then if we want to find the probability of testing positive, we just have to look at all the ones that give me a positive test results, right? Which are just underlined in blue here, which would be, should be this one, right? And this one, right? Because they both have T, yeah? That means test positive. And then we just know that our denominator would be equal to these two in blue added together, right? Yeah, and we'll see that's what we get here. Okay, next we have another conditional probability question, but this time it involves urns. So urn 1 contains 3 red balls, 4 blue balls. Urn 2 contains 4 red balls, 2 blue balls. A ball is drawn at random from urn 1 and placed in urn 2, and then a ball is drawn at random from the 7 balls now in urn 2. What is the probability that the ball drawn from urn 2 is blue? So the issue with this question we'll realize is the probability that the ball being drawn from urn 2 being blue, that actually depends on what ball we draw from urn 1, right? Because if we draw a red ball from urn 1 versus if we drew a blue ball from urn 1, that will change the probability of the ball that we get drawn from urn 2 being blue, right? So what can we do? We can separate this into the 2 separate cases, right? So assuming we draw a red ball, which happens 3 out of 7 times, right? 3 out of 7, I'll write on the top here, 3 out of 7 times. If we drew a red ball from urn 1, we'll see that urn 2 initially contained 4 red, 2 blue. If we drew a red from urn 1, this will now become 5 red, 2 blue, right? So if we're going to get a blue from urn 2, it would happen with a 2 over 7 chance, right? Then we add the case where we drew a blue ball initially, right? So 4 over 7, right? 4 over 7, now we have an extra blue ball in urn 2. So instead of 4 red and 2 blues, it's going to be 4 reds, 3 blues, right? And the probability of getting a blue from that is 3 over 7. So we just add this stuff together and then we'll get the probability for question 1. Yeah, so once again in these solutions, we go with the tree diagram method, but in an exam, it's unrealistic that we're going to draw all of this out. Probably a waste of time, but it just helps us, you know, understand what's going on, right? Yeah, so then we'll get that the final answer is 18 on 49 for this. Next, question 2. Given that the ball drawn from urn 2 is red now, what is the probability that the ball transferred was blue? So once again, remember P, A given B, identify B. B is, given that the ball drawn from urn 2 is red, that's B. And then my A, the event I want to find the probability of, is the ball that's transferred was blue, right? Once again, we can say that this is equal to P of A and B over the probability of B, yeah? P of A and B, how do we figure that out? That is essentially saying that the ball transferred was blue and the ball drawn from urn 2 is red, okay? So the ball transferred is blue, that happens 4 out of 7 times, right? 4 over 7, and then times the probability of us getting a red ball from urn 2. So once we've transferred a blue ball from urn 1 to urn 2, it becomes 4 red, 3 blue, right? From 4 red, 3 blue, if we want to get a red ball, it's going to be 4 on 7, right? And then all of this is going to be divided by my probability of getting a blue ball, right? Oh, sorry, no, the probability of getting a red ball from urn 2, right? Because that's what we're given, right? And then to figure that out, we can just once again, we can just take a look at the diagram here, right? So if we look at the notation here, R1 means the ball we drew from the first urn is red, B1 means from first urn is blue, and then similarly B2 means second urn blue, R2 is second urn red, right? So what we're interested in here is just adding up all the R2s, right? Because R2 means second urn red, right? So that would be 4 over 7, 4 over 7, 4 over 7 times 4 over 7, and then 3 over 7 times 5 over 7, right? We add these two together, right? I think, like that, yeah? And then that would be the probability of me getting a red ball, right? See, we have that on the bottom here, right? Alternatively, this is actually the exact same thing as, remember our answer in part A, which gave us the probability of the ball being drawn from urn 2 being blue, right? We could have just used what we had in part A, right? We could have just simply done this answer, but we do 1 minus that, so taking the complement of it actually, and this would give us the probability of us drawing a ball that's red, right? Because we figured out the probability of it being blue, we do 1 minus, it will give us it's red, because we only have red and blue balls here, right? It's a fair assumption to make. Sorry. Yeah, question 3 here. 3 here is asking us about whether these events are statistically independent. So A being this event that ball drawn from urn 1 is blue, and B being this event that the ball drawn from urn 2 is blue. And obviously, intuitively at least, we would think that these two events are very, they're very dependent on each other, right? Because drawing a blue ball in urn 1 is going to directly affect the chances of, or like, is going to directly affect the probabilities of getting a blue in urn 2, right? Because it increases the amount of blue balls, right? But then, like, is there like a mathematical way we can kind of prove this statistical independence, right? Matter of fact, we can, and we discussed this before. It's actually, we just want to show that P of A and B is equal to P of A times the P of B, right? But if this condition is not satisfied, then we know that these things will not be statistically independent, right? Because if this is, then they are. If it's not, then they're not, right? And we just calculate both sides of this equation here, right? Probability of A and B, which is equal to 4 over 7 times 3 over 7, and then the probability of A times the probability of B, which is 4 over 7 times 18 on 49. And obviously we see that these two results are not equivalent to each other, and hence we know that these two things are not statistically independent. Do we have any questions for this section, or is it all good? Okay, next section we have random variables, okay? Just quickly here, just the definition for random variables. I'm sure we all know what happens with random variables. I won't bore you with this complicated looking definition. Essentially, this tells you what happens here in random variables, right? We map the outcomes of random experiments to real numbers. For example, random variable x could be defined to map heads to 1 and tails to 0. So essentially, you can say that x counts the amount of heads when flipping a coin, yeah? Next thing, discrete random variables, right? Discrete random variable x such that s maps to r is discrete if its image, xs, such that s belongs to s, is countable. So we're just saying that discrete random variables are just random variables that are countable, okay? Next, we have the cumulative distribution function, the CDF, or like the abbreviation of it. What is a CDF? The CDF of a random variable x is this function denoted by capital Fx, given as fx such that real maps to real, where fxx is equal to p of x less than equal to x. This is very confusing. How can we understand this a bit more intuitively, maybe? Okay, so cumulative, right? What does cumulative mean? Cumulative means we kind of just add things up together, right? And that's exactly what we do for a cumulative distribution function. It is related to the probability distribution function in the sense that it adds up with the probabilities as we go, right? So the p of x being less than x is just saying I'm adding up all of my probabilities for x is less than equal to x, yeah? And then we have these following properties for my cumulative distribution function, right? So once again, remember my cumulative distribution function, I'm adding up probabilities as I go, right? So it only makes sense that if A is less than or equal to B, then capital F of A should be less than capital F of B, right? So this thing is not decreasing. Is there a problem? If A is less than or equal to B, then
I'll just sit here.
okay. Then my probability of x being between A and B should be equal to f of B minus f of A, right? And then as x approaches negative infinity of my cumulative distribution function, it should be equal to 0, because I expect that before I start adding any of my probabilities, I should start at 0, right? Before I add any probabilities together. And then at the end, when x approaches infinity, I expect that once I've added up all of these probabilities together, it should be equal to 1. Next, we have the probability distribution function, right? The probability distribution function just tells us all the probabilities associated with any random variable x's, right? So whenever x is equal to like a certain x subscript k, our probability distribution function just tells us that specific given probability, right? And note that our probability distribution function, this thing is only valid when it satisfies these two conditions, right? If and only if these two conditions are satisfied. So pk larger than or equal to 0 for all k just essentially means that all our probability is larger than or equal to 0, otherwise non-negative, and all of my probabilities add up together is equal to 1. Also technically, doesn't say here, but also all my probabilities should be less than or equal to 1 as well. It wouldn't make sense for a probability to be larger than or equal to 1. And then the cumulative distribution function, how is it related to the probability distribution function? This is in context of discrete random variables. In discrete random variable case, my cumulative distribution function is equal to the sum of all my probabilities for x is less than or equal to k. Okay, next we have the expected value, okay? The expected value, or otherwise known as mean, of a discrete random variable is a weighted sum of outcome values given by this formula here, right? So it's essentially saying, let's see, every xk has a probability of pk occurring, right? If I want to find my expected value of x, I simply multiply all of these multiply all of these possible outcomes xk by their respective probabilities to give this weighted outcome, right? It's weighted in the sense that things that are more likely have a higher weighting and hence like a higher probability, right? So when I add all of these things together, I expect to get the mean value. So essentially, if I repeat this experiment multiple times, it will tend towards this mean value or this expected value here. Theorem, expected value of a function of a random variable. So this is saying like when we have another random variable that is defined in terms of a variable we know, like for example, our random variable y is equal to g of x, we say that the expected value of y is equal to the expected value of gx, which is equal to all of my data points from my e of x, which is xk for all k, and then I evaluate all of that in the function g first. And after evaluating all of those functions in G, after I evaluate all of these data points, I multiply it by the probability again and sum it up across all k, and that gives me the new expected value. Okay, next we have the variance. Variance of a random discrete variable mean, mu, is the expected value of the squared deviations from the mean given by this formula. Variance x is equal to expected value of x minus mu squared, which is equal to sigma squared. Essentially what the variance measures, it's a measure of the average spread from a data set, right? We take all of our possible points on my data set, I subtract mu from them, and I square it, and I take the expected value, which gives me kind of like the average spread of this data, right? It just tells me like how far spread apart my data is. The larger this variance is, the more spread apart my data is. The less the variance is, the less spread apart my data is. And the standard deviation of x is just the square root of the variance. And my variance x actually has another formula, which is equal to e of brackets x squared minus brackets ex brackets squared. So these two are not the same thing. Just keep that in mind. And this is also an alternate formula. Usually when you're calculating variance, it will usually be much easier if we use the second formula here. Okay, next we talk about the scaling and shiftings of random variables. So for these random variables, essentially when we multiply them by constants, add constants to them, the expected values, variances, standard deviations are still related to the original ones in some sort of way, right? For example, the expected value of ax plus b. Firstly, let's just talk about this plus b here, right? So essentially all my data points have been shifted up by a constant b, right? So my expected value, as I expect, should be shifted up by some constant b, right? That should intuitively make sense. If all my data points here are multiplied by some constant a, it should also make sense that my mean would be also multiplied by this constant a, right? Expected value is fairly intuitive. Variance, ax plus b. If I add b to all of my data points, you can see how that doesn't really change the spread of the data points, right? Because they've all been moved by the same amount, right? But when I times it by a, when I times my data set by a, you'll see that this should actually somewhat increase the spread, increase or decrease depending on what a is, but it would change the spread of my data set, right? Because I'm multiplying all of the data by a certain constant, right? And we'll find that this is actually just equal to a squared times variance x. And then obviously for the next part, the standard deviation, we'll see that if we just take the square root of our previous equation, we'll just get the standard deviation equation there, yeah? Next up, we have Bernoulli trials and process. So a Bernoulli trial occurs once. We only have two possible outcomes. P is success, Q is failure, Q is equal to 1 minus P. Important thing, Bernoulli trials only occur once. Bernoulli process. It's a sequence of identical Bernoulli trials. So essentially we're just repeating multiple of these Bernoulli trials, right? Where the events Sk of a success on the kth trial are mutually independent, which is to say, me repeating this event multiple times does not change the probability of my successes or my failures. Every time I perform this Bernoulli trial again, they are always the exact same. Same probability of success, same probability of failure, nothing ever changes. And then next we try to count the number of successes in a Bernoulli process, right? Let x be a random variable that gives the total number of successes in a Bernoulli process consisting of n trials with probability p being success. Then the probability of x being k, so in other words, I want k successes, it would be equal to nck times p to the k times q to the n minus k. Essentially, just quickly, if I explain this, p to the k, because k successes, so obviously I need to have my p k times, q to the n minus k, because I want exactly k successes, right? I don't want any more than that. That means all of my other trials must have been failures, right? I have n trials total, I already had k successes, n minus k, that's my failures, nck, just to choose all the possible arrangements for my successes and failures. Okay, and next we have binomial distributions, which is actually quite related to the Bernoulli stuff we had before. The binomial distribution with n trials and probability p success is this function b n pk, b standing for binomial here, is equal to nck, p to the k, times 1 minus p to the n minus k, for k is equal to 0, 1, 2, all the way to n, right? So basically if we sub in k, if we sub in a value for k, it just gives me the probability of, like, for example, k is equal to 0 gives me probability of 0 successes, k is equal to 1, probability of 1 success, k is equal to 2, probability of 2 success, and so on. Expected value and variance, right? So if x is a binomial distribution with n trials and probability of p success, that's just what it means. N here, the first value is always the amount of trials, second value gives you the probability of success. Yeah, so when you see that, that's what it means. And we know that there's formulas for my expected value and variance. And my expected value should just be my number of trials times my probability of success. That should be easy to understand. Variance is npq, which is also equal to np times 1 minus p. And here we have an example with a biased coin. So we'll see what happens when we have a bias coin. In this bias coin, you have a probability of heads being 0.7. It costs $5 to enter this game. The coin is flipped 12 times and you win $3 for each head. Every flip is independent of the other flips. Let X be the number of heads in the 12 games, or 12 flips, sorry, and let Y be the net amount you win after playing the game once. And you want to calculate expected value of Y and the variance of Y. First thing to notice in this question, you should always be asking yourself like why question makers do certain things, right? In this question, they define 2 random variables, which is kind of strange, right? If you only needed 1, they would have only defined 1 for you, right? X is the number of heads in the 12 flips, and Y is the amount you win after playing the game once, right? Is there any relationship between these 2 variables? I think there is, right? Y, which is the amount I win, should be equal to 3 times X, which gives me the amount I win for like getting X amount of heads, right? 3 times X, because $3 for every head, 3 times X gives me the amount of money I win. But we also have to account for the amount of money we need to enter the game, right? Y is equal to 3x minus 5, yeah? Now to find the expected value, we just take expected value on both sides, right? Expected value of Y is equal to expected value of 3x minus 5. So EY is equal to E3x minus 5, which is equal to, remember the scaling shifting laws from before, 3 times E of x minus 5, right? And then now it's just a problem of finding E of x, right? Note that this is a binomial distribution. We either get a heads or we get a tails. That's my success versus my failure. Success with 0.7, and we have 12 trials, right? EX is equal to NP, which is equal to 12 times 0.7, right? If we look down the solution, that's exactly what we have here, right? 3 times NP, 3 times 12 times 0.7, minus 5, that gives me my EY, right? And then, well, we also talked about this before. How does the variance shift? We ignore the constant term at the end, right? We just have to figure out what the constant term is before my random variable, and then we just take it to outside and square it, right? So 9 times variance x. Variance x, what is this equal to? It is equal to NPQ or NP1 minus P, right? Where n is equal to 12, p is equal to 0.7, yeah? And then that's how we figure out the variance there. Okay, next we have a geometric distribution. The geometric distribution, you can have a read here, but essentially what it does is just measures the probability that it take, or like the probability of taking X amount of turns or K amount of turns before I get a success. So, for example, if I needed, like, if I wanted to calculate the amount of turns it would, sorry, if I wanted to calculate the probability of getting my first success on the 4th turn, I'll just sub in K is equal to 4. If I want to find the probability of me getting a success on my first success on the 5th turn, I just sub in K is equal to 5. And that's essentially what it does. It gives you the probability of finding your first success on the Kth turn. We'll just note quickly that geometric distribution also is a valid probability distribution. And then the expected value and variance is also shown here. It's probably a bit harder to derive, but it is definitely doable. Next, we have sign tests. Sign tests, as we see here, they just decide whether a comparison between 2 sets of figures or a set of figures and a standard can be assumed to be pure luck, or if there is some evidence of a difference between these 2 sets or the set and the standard, right? What does that really mean? Well, we'll see with this example, right? So with this example, we have algebra and calculus students here, right? We want to figure out if students being better at algebra than at calculus, if this is like a myth, or is this pure luck, or is this actually something that's like legit, like, oh, people are actually better at algebra than calculus, and I can say this like fairly confidently, right? That's why we use these sign tests, right? What does the sign test measure? The sign test measures the amount of algebra students that do better than calculus students, right? Or like better than or equal to at least. We'll see that here. This algebra student did better. This one did same. This one did better. This one we can skip because he did worse. Next one did worse. This one did better, worse, better, 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 same, better, right? So in total there were 15 students here, and 12 of them did better or the same as the calculus students. And we figure out, like, assuming that this is completely random, there's like a 50% chance that an algebra student does better than a calculus student, right? Assuming that these tests are like equal or like fair, right? Or like not fair, but as in like it's just random, right? There's no like skill involved or like easiness involved, right? We figure out what is the probability of this thing happening, right? The probability of this thing happening is given by this probability of x being larger than or equal to 12 for this binomial distribution. We just sub all of these values in. We just go from k is equal to 12 to 15. We add it up. It's equal to 1.67%. And in this question, we define a threshold for being pure luck as being 5%. So anything under 5%, we'll consider that as not being pure luck, because there's a very small probability that it could have happened, and hence we don't assume that to be pure luck. And then here we say that it's very unlikely the difference is pure luck, and hence the students are probably better at algebra than they are at calculus. Okay, next we have the probability density function. So it's called density function for continuous random variables, but it's called a distribution function, or just for the probability part, it's called a probability distribution function for discrete random variables, but a density function for continuous random variables. And a random variable is continuous if and only if the cumulative function fxx is continuous, right? So it just means that the variable can take all the possible values that cover this interval of the real line, right? That's what essentially the definition of a continuous random variable. You can't count it. It can take literally any value. Like, let's say my interval was like 0 to 2. It can be 0.1. It can be 0.01. It can be 0.00001. Like, you can just keep going. So it's impossible to count. If x is a continuous variable with this cumulative function fx, then the probability density function is defined by fx equals to f dash x, or capital F dash x. So my probability density function, which is given by lowercase f, it's equal to the capital F x, but I have to take the derivative of that if x is differentiable at x, right? But it's also not really an issue if it's not differentiable. So for example, it's also equal to fx is also lowercase f x is equal to the limit as x approaches a from the negative of f dash x if my f is not differentiable at x is equal to a. So if it's not differentiable, that's not an issue. As long as this limit exists, it's still fine. Next, we have some properties of probability density functions. You'll see that these are essentially very similar to what we had before, right? So fx larger than or equal to 0 for x belonging to real numbers. So this just means all my probabilities are larger than or equal to 0, right? It's just fairly simple. Capital Fx is equal to the integral from negative infinity to x of ft dt, right? So essentially my ft is my probability density function. When I take the sum from negative infinity to x, that's the same as evaluating my integral at the point x, right? Next, if I take the integral from negative infinity to positive infinity of my probability density function, it should be equal to 1, right? Summing up all the probabilities, it will be equal to 1. If a is less than or equal to b, and then the probability of a, b, or x being between a and b is equal to the probability of, so you see here that the only difference between those two is the equal sign there, right? So yeah, this is less than or equal to, but this one is just less than, right? You think that there's a difference, but no, not really, because this is a continuous distribution. In a continuous distribution, let's say my probability density function kind of look like this. If you ask me to give you the probability of some specific event, like let's say this is like 2, right? If you want me to give you the probability of 2 happening, like, it's just impossible. Like, I can't tell you what that probability is. It's probably just 0, right? Whereas if you give a interval, like let's say I give you an interval from 2 to 3, right? I give you an interval from 2 to 3, and I want you to find this probability. So P of 2 is in between x is in between 3. I can now actually give you a probability for this, right? Because then I can just take the integral from 2 to 3, and then whatever that value is, that'll give you the probability, right? Next, so the expected value of probability density functions, right? So similar to before, we'll notice here that integration kind of acts in the same way to the thing before, where I had the capital sigma sign, and I added up all of those things together, right? Integration is essentially doing the same thing. We're adding up all of these continuous, like, random variables. We're adding them all up together using integration, right? And then how do we find the expected value? We multiply my probability density function by x, because x is my value point, right? Whenever I do x times f of x, that's like the weighted sum that we had before, right? But instead of a discrete random variable, it's now continuous, which is why we have to perform integration on this, right? And then similarly to before, with the expected value of a function of a random variable, it's simply like, instead of the x, we just take that x and we evaluate it through my new function first. So g of x, I evaluate it there first. I multiply it to my probability density function, and then I take the integral from negative infinity to infinity. Variance, standard deviation, and all of this scaling and shifting works the exact same way as my discrete random variable. Yep, so here are some examples for this. Continuous random variable x has the probability density function given by fx equals to alpha times 1 minus x squared, for 0 is in between, x is in between 1 and 0 otherwise. And you want to find the value of alpha, right? So how do we find the value of alpha? We know the integral from negative infinity to infinity should be equal to 1, right? But negative infinity to infinity is not a very suitable range for this question, right? Because we know that it's 0 other than, or the probability function is equal to 0 other than 0 to 1, right? So the relevant range in this case is just 0 to 1, right? So we can just take the integral of this function from 0 to 1, and that should be equal to 1, right? We equate that to 1, and we see what alpha is equal to, right? So we'll see here, we take this integral from 0 to 1, we integrate this, we get 2 over 3, so that means 2 over 3 times alpha equals 1, alpha equals to 3 over 2. With this value of alpha in mind now, we can evaluate the expected value of x and the variance of x, right? How do we do this again? We multiply it by x, right? For expected value, right? For expected value, we multiply by x, take the integral from negative infinity to infinity, but in this case, we only have to do 0 to 1, right? 0 to 1, we get expected value is equal to 3 over 8. And then remembering the definition we had before for the variance, right? Expected value of brackets x squared minus brackets expected value brackets squared, right? Remembering that thing. So the expected value of x squared is just x squared times the probability density function, and then ex squared is whatever the result we had from before, so 3 over 8, this is my ex, right? And then I just square that result, right? And I subtract these two, and then we find that the variance is equal to 19 on 320. Is it all good? No issues? Okay. Next, for probability density function, there's this idea of standardization. So if ex is equal to, so my expected value is equal to mu, variance x equals to sigma squared, then the random variable z is equal to x minus mu and sigma is the standardized random variable obtained from x. This z is essentially, I don't know if you guys heard this before, you probably encountered this in high school maths. Z stands for z-score. So the z-score is a part of the standard normal distribution. The expected value of z is 0 and the variance z is 1. We'll go here, I think, yeah, it explains later why we do this, but here's just a definition: continuous random variable with probability density function. Just complicated looking function. Essentially, this is just the normal distribution. This is what a normally distributed function looks like. In this case, it has mean mu, variance sigma squared. But the issue with this, as we'll see in the next slide, is that integrating this function is very tedious. It's very annoying. So whenever my mu and sigma values change, I have to think of a new way of integrating it. And even integrating it at the start was very difficult. At this stage, we can't really do it, right? At this stage, what we do is we use the table, right? but the table only gives us the values for the standard normal distribution, right? It doesn't give us the values for any of these other normal distributions, right? So what we try to do is, with all of our normally distributed functions, we try to standardize them first, right? We try to make them into the standard normal distribution form by using the z-score, right? With all of my variables here, for example, p of x being less than or equal to x, assuming that x is a normally distributed random variable, I can find the z-score by doing minus mu on sigma. I do on both sides. Capital X minus mu on sigma is just becomes my z-score, and then that becomes probability of z being less than or equal to lowercase x minus mu on sigma, so here. And then essentially all we just have to do is evaluate it, or like it would be equivalent to evaluating this integral here, but I'm sure we've all seen how to do this. This thing we can simply do using the standard normal distribution table, right? Gives us all the values. Okay, some examples. Mo's mobile phone company produces phones with an average lifetime of 4.2 years. Suppose that the lifetime is approximated normally, so okay, this is a normally distributed random variable, standard deviation 1.3 years, right? Just a quick thing, what happened to me before was I always got standard deviation and variation confused, sometimes forget to square root the variance. The question gives me variance, I forgot to square root it, but just keep that in mind. Always be careful with what they give you. Anyway, standard deviation 1.3, average lifetime 4.2. He wishes to offer a warranty on his phones, but it's only profitable for him to do so if he replaces his fuel within 2% of the stock he sells. What warranty length should he offer, right? So the problem here is that like, so his average lifetime is 4.2. Ideally, you would want to advertise as high of a or what do you call it, lifetime as possible, but that is not very like good for the business, because the higher warranty length you offer, the more cost you're going to incur, the more phones you're going to replace. He wants to replace fewer than 2% of the stock he sells, so basically less than 2% of his stock should last less than his warranty length, right? And we're just trying to figure out what should this warranty length be, right? So let's say I let this warranty length be t, right? In other words, what this question is asking me to do is I want to find the probability of x being less than or equal to t. So my random variable x, I want this probability to be less than 0.02, right? If this occurs less than 0.02 of the time, he's happy, yeah? But the issue is, how do we figure that out, right? What we do here, we standardize it, right? We can standardize it on both sides, remember, minus mu on sigma. So on the left-hand side, this pretty much just becomes z after we perform this. And then on the other side, we substitute in our actual values of mu and sigma, which is 4.2 and 1.3. And we get the probability of z being less than or equal to t minus 4.2 over 1.3, right? And then all we essentially have to do from here is we go into the table, we find the probability that corresponds to, or we find the z-score that corresponds to a probability of 0.02, right? We'll see that from the table, this z-score would be equal to negative 2.05, just to be the closest, so that's why we use this. Then we get t minus 4.2 over 1.3 should be roughly equal to negative 2.05. So then t is equal to 1.535, yeah? So that's why we should probably be doing a warranty length of 1.535 years, despite having an average lifetime of 4.2. Okay, and then here we have normal approximation to the binomial distribution, right? So normal distribution, remember, is a continuous distribution, right? Binomial distributions, on the other hand, they are discrete, right? So we're trying to use a continuous distribution to approximate a discrete distribution, right? And we'll see that there are actually some problems to this. So the problems to this is this thing, continuity correction. This pretty much sums up what the problem is, right? The issue. In a continuous distribution, right? You'll see on like this curve, there's a smooth line drew over the graph, right? But like, for example, at this point 10, right? If I wanted to find the probability of x being larger than or equal to 10, right? And I plugged this thing, I did all of my due diligence, I standardized it, I made it so that it's normally distributed, I found the correct Z scores and stuff. But the issue is the value of 10 goes up to is exactly here, right, on this graph, right? The probability of x being larger than or equal to 10 separates the 10 like this, right? And it actually gives me the probability of everything from here onwards, right? That's what it gives me. But what I actually want, instead of that, is I just want it to include the entirety of 10, like this, and everything onwards, right? That's what I want to get, right? So how do we change that, right? How do we change that? That is actually a good question. We'll notice that for my binomial distribution, each of my value points, for example 10, it actually lies between 10.5, this is kind of thick. It lies between 10.5 and 9.5, right? It lies between plus minus 0.5 of the actual value, right? So 2 would be between 1.5 and 2.5, 3 is between 2.5 and 3.5. So if I want to find the probability of x being larger than or equal to 10, after I apply my continuity correction, this would actually be probability of x being larger than or equal to 9.5, yeah? And whereas if I wanted to find the probability of x being larger than 10, this is actually a different case, right? We know that for continuous, probability of x being larger than or equal to 10 versus probability of x being larger than 10 is exact same, because probability of x being 10 is just 0. But that is not the case for discrete, right? Discrete random variables is different. So in this case, I would have to do probability of x being larger than 10.5 instead, right? And that's the continuity correction stuff, right? On the table here, you just see all of pretty much all of the possible different cases that you'll get. But yeah. Okay, we have a question here about normally approximating a binomial distribution. Australian No Hopers Party claims that 6% of voters support them, and in a survey, 500 people asked about voting intentions. We assume the claim is true. We let x be the random variable, giving us the number of voters, and x is modeled by a binomial distribution. Find mean and variance, okay? Find mean and variance, not that bad, right? NP1 minus P, right? NP1 minus P. 30, 28.2, right? There's nothing difficult. We just have to identify what n is, identify what p is. Everything else follows easily. When the survey results are published, it is found that 22 of the people supported the ANHP. Use the normal approximation to the binomial to estimate the probability that x is at most 22, right? X is at most 22. What is that? Probability of x being less than or equal to 22, right? But once again, remember we are dealing with a discrete distribution, right? And we're trying to make it normally approximated. So we've got to apply the continuity correction, right? After applying continuity to correction, this is equivalent to the probability of x being less than or equal to 22.5, right? And then we'll see that in the solutions here, right? We say that essentially after the continuity correction, we go from here to here. We get probability of x being less than or equal to 22.5. I do my same standardization as I did before. I obtain my z-score and I say, oh, I want the probability of my z-score being less than or equal to negative 1.41233, right? The issue with this is sometimes on the tables it doesn't give you the values like this, right? It only gives you the positive results. Basically on the table it gives you p of z being less than or equal to let's say, I'll just say k, if k represents all of these like possible z-scores. Usually it only gives it for when k is a positive number, and it always gives it in this way, the probability of z being less than or equal to k. It doesn't give you usually doesn't give you z being larger than or equal to k, it only gives you z being less than or equal to k, but that's fine because these are actually inherently related to each other, as we'll see here, right? So firstly, we flip the sign, and we flip the from this step to this step, we flip the sign, and we flip the inequality sign, right? Because we know that this normal distribution thing, it's an even function, right? So my z-score being less than or equal to negative 1.41 is the same as my z-score being larger than or equal to 1.41. And then next, I say my probability of z being larger than or equal to 1.41 is equal to 1 minus z, p of z being less than or equal to 1.41. And this is just a complement, right? We already discussed this before, it's just a complement. And then we find the corresponding value of this in the table, we sub it in, and then we get our answer here, right? 0.0793. Okay, I think this might be the last section here. Yeah, so this is the last section here. The exponential distribution, continuous random variable t with probability density function f, reals to reals, ft is equal to lambda e to the negative lambda t. Essentially, it's just another different distribution, same thing as we learned before, it's just another distribution that you need to know. Exponential distribution will have expected value of 1 over lambda and a variance of 1 over lambda squared. Okay, so here we have a question. Suppose the life of a car battery of a certain brand has an exponential distribution for which the mean is 60 months, okay? Blah, 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 blah. And then for the first question, you want to calculate the probability that the battery life has run out within the first 2 years, right? How do we do this? We just take the probability of it running out between 0 and 24 months, right? So remember my probability, it follows an exponential function, right? The probability of running out follows an exponential function of lambda e to the negative lambda t, right? In this case, my lambda would be equal to 1 over 60, right? Because my expected value is 60, right? And my, e is equal to 1 over lambda is equal to 60, e of x, sorry. Yeah? Lambda is equal to 160. Then we put this in, and we take the integral from 0 to 24, right? Because that will give me the probability of it running out anywhere from 0 to 24, right? And then we do this integral, we figure out it's equal to 1 minus e to the negative 24 on 60. And then the next part is a very similar idea. They challenge you to find the probability that it runs out between 2 and 4 years, right? 2 years is 24 months, 4 years is 48 months. We do the same thing again, except we integrate between 24 and 48. Okay, so 24 to 48 of the exact same function, and then we get this value. Okay, and that pretty much sums up our revision seminar for today. Lastly, we just have a special gift for everyone. If you scan this QR code, there's more revision sheets up there that you can try out for yourself. And I'll just leave this up here for a while if you guys want to get the revision sheets. If you guys also have any other questions, you can just ask me now. Otherwise, sorry?
Can you download this live?
Yeah, probably. I'll ask them to upload the slides as well. Are you in the MathSoc server?
Yeah.
Yeah, okay. I'll ask them to upload the slides after as well. Yeah, that's not an issue. Alright. Other than that, if anyone has any questions, you can just come up to me and ask me as well.